We continue review linear algebra. Compute the determinant of the matrix by cofactor expansion. Well, this will be very easy and straightforward. Of course, we can use the calculator as well, but just do it by hand first. So using cofactor expansion, meaning we're going to choose any row or any column. And then let's just, in this case, let's choose the first row. Let this matrix be an A, so we have determinant of the matrix A equal to, right, we have -1, 2, and -1. For -1, and we're going to take that -1 times the cofactor of that element, meaning we're going to cover the row and the column of that. So what we have left is 3, -2, -4, and -1. Right. But not only that, it is only the minor. Remember, we also have to have the sign chart. Start with positive and alternating sign from every direction, like a chessboard. So the -1 stand on the plus side, so we should have a positive for that element. Next, the 2 stand on the negative sign, and then we have 2, and then we have a determinant of the submatrix. So we cover the row and the column that containing the 2. So we're left with 4, -2, -3, and -1. And then we have -1. The -1 stand on the plus sign, so positive. And then the submatrix, determinant of submatrix. So that is 4, 3, -3, -4. Right. So we have -1. Determinant here is -3. Let's just write everything down. 3 times -1 minus -4 times -2 minus 2. 4 times -1 minus -2 times -3 minus 1. 4 times -4 minus 3 times -3. Right, so 2 by 2 determinant should be easy. So -3 minus 8. Yeah, minus 3 minus 8. And then minus 2 minus 4 minus 4 minus 6. And then minus 16 plus 9 minus 7. So minus 16 plus 9. So we have 5 plus 20 plus 7, 32. Yeah, I check with the calculator. Second matrix, go to math. The first one is determinant. Just hit enter. The matrix 3 by 3. -1, 2, -1, 4, 3, -2, -3, -4, and -1. Right, they missed something. Right, let's check again. So -3, Okay, negative 3, negative 8. So it's negative 3, negative 8, negative 11. So we have 11. So that is 38. So simple enough. Next we find determinant. This is a 4 by 4. So as always, pick the row, the column that have the most zero. It is a lot easier to do it that way. So I'm going to pick the first column here. So let this matrix be a B matrix. So determinant of B. First, it's going to be negative 5. The sign chart, it starts from the plus, so positive, negative, positive, negative. So this negative 5, the coefficient, the sign is positive. And then we have the submatrix. So we're going to cover the row and the column that containing that negative 5. So we're left with negative 1, 2, negative 2, 3, 0, 0, negative 3, 1, and 4. And then we have 0, so the sign negative 5 and then minus 0. Actually, if it is 0, it doesn't matter what it is inside, it's going to be 0 anyway. And next, the 0 here is going to be plus 0. Doesn't matter what the minor or cofactor are, it's going to be 0. And then subtract another 0. Again, doesn't matter what the submatrix minor or cofactor are, that's going to be 0. So we just have that. Now this one going to be determinant. Once again, I'm going to choose this row because that have a bunch of 0. Now the side chart will reset again, positive, negative, positive, negative. So it's going to be negative, positive, and negative for those 3. Right, first I have negative 5, and then the negative 3. Okay, just put the bracket. Negative 3, negative 3, and then for 3 we cross out the row and the column that containing the 3. Right? So that will be 2, negative 2, 1, and 4. After that we have a plus 0. Doesn't matter what it is, it's going to be 0. And then subtract 0. Doesn't matter what it is, it's going to be 0. So bottom line is we just have this. Negative 5 times negative 3 is 15. 2, negative 2, 1, and 4. So 4 minus negative 2, so 4 plus 2 is 10. So 15 times 10 is 150. Right, so pick the row, the column with the most 0 in it. And then, of course, have to consider the sign chart. And then the determinant of the submatrix. Right. This is easier to check with the calculator, so we should do that. 4 by 4. Yep, so we're good. Right. Next, evaluate the determinant of this matrix. Well, if we have a star and star here, meaning that we cannot have put this in the calculator, so we have to have evaluate this somehow. So when we look at this, we see this one has a row 1 2 5 1 2 5, so we have the same row here. So if the rows are the same like this, so that means they are not linearly independent, and if they are not linearly independent, the determinant equal to 0. Let's say this is the matrix A. Right. So if we have the column or the row that are not linearly independent, determinant is equal to 0. So we have determinant equal to 0, and that is linearly dependent, meaning not linearly independent. Right. So that's why we have this case. What we have here is, again, the star is star. We cannot use a calculator, so we have to use this somehow. When we look at this, this is almost look like the upper triangular matrix. If this one is a 0, then this will be a lot easy to evaluate. If this is 0, then we just multiply everything in the diagonal and evaluate the matrix. So in that case, we have to use the row operation to turn that into a 0. So we, based on this pivot here, so I will multiply up to eliminate this. From 2 back to 1, we have to multiply by 1/2, and actually negative 1/2, and then we can add and substitute into row 4. To do that, we're going to have 0 here. Remember, this operation is the row replacement. Row replacement does not change the determinant. So if we do this, determinant stay the same. Meaning whatever determinant we have after that is the same as what we have before that. Right. So this is the 2 bar already. Sorry. If this is a 2 bar already, so that is the determinant already. We don't need to change anything. But if we want to write this is a matrix B, so when we do that, we have the first row stay the same, even the third row stay the same. Right, negative 1/2 times 2 is negative 1, plus 1 is 0. Negative 1/2 times 1 is negative 1/2, plus 7, just say 6.5. Right, negative 1/2 times 1 is negative 0.5. Negative 0.5 plus 7, 6.5. And now this is an echelon form matrix, or we say upper triangular matrix. We have all the pivot, and so determinant of this is just the product of all the diagonal entry. So determinant of B equal to 1 times negative 2 times 2 times 6.5. 6.5 times 2 is 13. 13 times negative 2 is negative 26. Right. So once again, when we do this row operation, the determinant will stay the same. And so determinant of this matrix is negative 26, which is the same as determinant of that. Right. times 10. Right. So if A is this matrix, find determinant of 2 times A transpose. So first, if this is A, we find determinant of the matrix A. So just cross multiply and subtract. So that's going to be 4 minus a negative 6. So 4 plus 6 is 10. Now we want to find determinant of 2 times A transpose. Right. Now first, A is a 2 by 2. So A transpose is also 2 by 2. So why is that important? Because determinant of a number times a matrix is equal to whatever that number is raised to the dimension. This one has 2 rows, so times the determinant of the matrix. So we have 4, and determinant of the matrix transpose is the same as determinant of A. So that gives us 4 times 10 is 40. So in this section we use this problem we do use 2 properties here. The first one is if A is an n by n matrix, then we have determinant of A determinant of number constant times A is equal to that constant raised to the power of n times determinant of A. So C to the n times determinant of A. So in this case, determinant of 2 times A transpose is 2 to the second determinant A transpose, because A transpose is also 2 by 2. And then of course, so this is the first property. If we multiply a number to a matrix, determinant will be equal to that number raised to a number of row or number of column, because A have to be a square matrix. So that number raised to a number of row times determinant of the matrix. So that's the first one. The second one is easier. Determinant of A is equal to determinant of A transpose. So we use those 2 properties. Right, next, also more properties. Let A and B be matrices such that determinant of A is 5, determinant of B is negative 20. Find determinant of A inverse times B. Right, so, and first the properties. Determinant of a product is the product of determinant. So that's another property. And then determinant of the inverse, if it exists, equal to 1 over determinant of the matrix. So those are some useful property of determinant. So in this case, determinant of A inverse B equal to determinant of A inverse times determinant of B. Determinant of A inverse is 1 over determinant of A times determinant of B. So pretty much determinant of B over determinant of A. Determinant of B is given negative 20. determinant of A is 5, so negative 4, that is timestamp. Right, next, using the Cramer's rule to solve the system of equation. So in this case, very simple. First, we calculate all the determinants. So the D is the coefficient matrix, determinant coefficient matrix 2, 3, 3, and negative 2. Just calculate the determinant. Negative 4, negative 9, negative 13. Next, we're going to have dx, or in this case, the first column. So d1. So what we do here is we're going to substitute the this coefficient into the first row, first column. Sorry. Into the coefficient matrix. This is d1. So 28 times negative 2 minus 3 times 3. Right. 28 times 2, 56. Negative 56 minus 9. 56. Sorry, negative 56 minus 9. So 56 plus 9, 65 negative. And then we calculate D2. So we will substitute into the second column here, 28 and 3. So we have 2 and 3. So 2 times 3 minus 3 times 28. 3 times 28 is 84. Negative 84 minus 6, so 78. Right. And then finally, we have x equal to the x over d and y equal to dy over d. So dx, in this case, we don't have x and y, we have x1 and x2. That's perfectly fine here. X1 is d1 over 2, x2 is d2 over d. Yeah, just we understand when we substitute the coefficient by replace the large column, we have the different determinant. Right, so d1 negative 65 divided by negative 13, so that is 5, and x2 negative 78 over negative 13, that's 6. So I have x1, x2 is 5 and 6. Right. Next, use Cramer's rule to solve for x. And at this time we said we can use Cramer's rule to find determinant. But we still need to show that first find d is the determinant of the coefficient matrix 5, 4, negative 1, 1, negative 3 and 4, 2, 1 and 1. Right, and then we have dx or d1, which replace this coefficient. Say this is d, call that dx. I replace the last column 28, 32, and 22 into it. Right, now just find determinant. So the reason we should use a calculator on this one, you'll see in a minute. First we have a 3 by 3. Right, 5 and 4 and negative 1. 1 and negative 3 and 4. 2 and 1 and 1. Right, we have negative 14. And now for this one, of course we can do all that all over again, but I recommend we highlight it, hit enter, so that copy and paste, and all we do is just replace the number here. 28, 32, and 22. Yeah, that will be better. Negative 70. And finally, x is equal to dx over d. Negative 70 divided by negative 14. It is going to be 5. Yeah. So the Cramer's rule, the only nice thing about that is we can calculate just solve for one variable. Timestamp. Now, determine the parameter s for which the system has a unique solution and describe the solution. So in this case, we should use the Cramer's rule here, because row operation with the variable like this is difficult. Inverse is even worse. Right, so first compute d s negative 7, 3, negative 21s. So negative 21s squared plus 21s. Right, if we want solution, this have to be different than 0, right? Because the x is dx over d, and we don't want to divide by 0. Divide by 0 is undefined. So that's not equal to 0. So it's easy. We factor out just factor out the whole thing. Negative 21s, then s minus 1, not equal to 0. So s have to not be 0, or s not equal to 1. So we need to have that. Otherwise, this is 0 or that is 0, which we don't want. We don't want determinant to be 0. Right, so that is d. Next, we solve for dx. On this case, d1. So just replace the first column by 3 and 5, the last column, into this, so we still have negative 7 and negative 21s. So that gives us the determinant of this equal to negative 63s plus 35. And then d2 we'll replace the second column by 3 and 5, and then we still have s and 3. Right, so determinant of that is 5s minus 9. Right, and with that, So with that we have x1 is d1 over d and x2 is d2 over d right. So that's what we have. Timestamp. Actually, I go back and check the problem. I forgot an s here. So negative 21 s squared minus 21s. So that one's good. Yeah, I don't know why that turned out right when I copied this wrong, but I do miss an s here. So that gives us negative 63 and 34, 35. So that is 28. S. So sorry. So this would be negative 28s. And of course, if it is, we can cancel an s and an s cancel on minus and minus here. So bottom line, the x1 we can write as 28 over 21 s minus 1. Sorry, it should be that. I forgot the s here. Right, so right, so sorry about that. Right. Next, calculate the area of the parallelogram with given transformation. So first, we're going to sketch this parallelogram. It has 0, 0, 2, and 6, 8, and 10, and then 6, and 4. So for this one, what we do is try to calculate the area of the unit square S into the parallelogram P. So the unit square is just 0 to 1, 0 to 1. Of course, we can choose anything, but there's an advantage of using the unit square. We'll see in a minute. Right, so now we will find the transformation that transforms S into a parallelogram. Now, let's go way back in the first part of this review when we're trying to find the transformation, the matrix of a transformation. By the way, if we can write as A of X is equal to T of X. So we're trying to find a matrix representation for the transformation. So the way we do that is we look at this point, which is 1 and 0, which is E1, and this is 0 and 1, which is E2. So E1 and E2 is E1 and E2 form the identity matrix. So E1, E2, right? So in that case, we just assign the transformation so that the orientation will preserve the clockwise orientation, that is. So it will map 0 to 0, it will map this point to that point, and it will map this point to that point, right? So in particular, what we have is T of E2. We map to this one that's 2 and 6. T of E1, we map to this point of 6 and 4. Because of that, the matrix A will be just the matrix of T transform E1 and then T transform E2. So TE1 is 2 and 6. I'm sorry, TE1 is 6 and 4. And TE2 is 2 and 6. So determinant of A is 6 times 6 minus 4 times 2. So that is 36 minus 28. Sorry, 36 minus 8, which is 28. And finally, find the area of the parallelogram P, which is equal to T of S. So we have determinant of P. I'm sorry, this is not determinant. We want the area, right? Right. So we want the area of the parallelogram P, which is the area of the transformation of S. What we have is the important properties of the area of TS is equal to determinant of A times the area of S. So the area of S times the determinant of the transformation, 28. So in this case we have the area of that equal to determinant of A times determine the area of the pre-image. Determinant 28, the area of the pre-image of the unit square 1 by 1 is 1. So that's what we have, 28. So the area of the image is equal to determinant of the transformation times the area of the pre-image. Just so that we need to one more thing, determinant could be negative, so we just put the absolute values there to guarantee things will be positive. This case we don't have to because it's already positive. Right, just keep that in mind. Area must be positive. Right, so timestamp. Next, we have two examples, two applications of determinant. So in this case, there's two examples. We use determinant to calculate the area. Right, so the area is plus or minus. The reason of plus minus is the same thing as I mentioned on the previous form. The area needs to be positive. So determinant could be positive, could be negative, but we just throw the net plus or minus there. It could be plus, it could be negative, whatever give us the positive area. Right, so appropriate sign should be chosen to yield a positive area. So that's what we have. Right, so in this case, if we want to find the area of a triangle, we're just going to use plus minus 1/2, first point, second point, and third point. So just like that. Right, these are the points 10, 4, 3, -5, -7, and -4, and 1, 1, 1. Right, so just like that. So we just going to use cofactor here, or just use the calculator. Right, so we have negative 97, which is determinant. By the way, the two vertical bars for determinant. So we have plus or minus 97 over 2. Obviously, we have to choose the side, so we have positive. So we say the area is 97 over 2. Right. So this is an application of determinant. Right. So be that. Next, we also have another application of determinant, but kind of in the sense is come from this. Now it says that if this equal to 0, so that means the points are collinear, meaning that they're on the same line, and that makes sense. Imagine if you have 3 points, where 1 point, 3 points stay on the same line, so they are collinear on the same line. Then there's no triangle are formed from this, so the area of this triangle could be 0 because there's no triangle on the 3 points on the same line. So that makes sense. If this is equal to 0, the area is 0, so there's no area or there's no triangle, meaning they're on the same line. So that's straightforward here. Just going to put the point in that. One, negative 1, 10, and 1, 0, negative 9, and 1, negative 2, 30, and 1. And is this determinant equal to 0? If it is, they're on the same line. Right, I'm just going to use a calculator here. Right, so we have the determinant of that equal to 1. So meaning there is a triangle, because the area is bigger than 1, so there is a triangle forming from these 3 points. If there is a triangle, they are not collinear. So because not equal to 0, the points are not collinear. Just say are not on the same line. Just collinear. Right. So with that, we stop the review here. See you in another video reviewing linear algebra. Thank you for watching.